Hello, my name is Anna Cepek, and I am a postdoc at the Institute for Basic Science, Center for Geometry and Physics in Pohang, South Korea. I'm interested in studying the topology of manifolds using configuration spaces of finite subsets within the homotopy-theoretic context of infinity categories by way of stratified spaces. So the tools used to do this can broadly be called configuration categories, but before I give any precise definitions, I'd like to give an indication of some of the directions that I'm interested in heading. So configuration categories can be used to understand the combinatorics of infinity n categories. They can be used to decompose the configuration space of a product of manifolds into terms of the configuration spaces of the factors. They closely relate to EM algebras, and they can be used to study finite type non-invariants. So the configuration space of k points in a manifold M is the subspace of all k tuples of points in M that are pairwise distinct. There's an action by the symmetric group given by permuting the indices, and we can quotient out by this action and obtain the configuration space of k unordered points in M. Now, as we vary k, these spaces organize together into one topological space called the Ron space. So as a set then, the Ron space is simply the collection of all finite, non-empty subsets of M, and we endow it with the finest topology for which the maps as indicated are continuous for all k greater than or equal to 1. Observe that by remembering the cardinality of each point in the Ron space, this gives us a map to the natural numbers, which endows the Ron space with a structure of a stratification. So in general, a stratified space is a paracompact Hausdorff topological space X, a partially ordered set P with the upward closed topology, and a continuous surjection from X to P, such that the fiber over each point is connected. These fibers are called the strata of the stratified space. So in the case of the Ron space then, we can observe that its strata are precisely the configuration spaces of unordered points in M. Now, the homotopy type of these configuration spaces are encoded as the maximal subinfinity groupoid of what's called the exit path infinity category of the Ron space of M. So in general, the exit path infinity category of a stratified space X has objects, it's just the points in the space X, and morphisms are paths in X that exit. So an exiting path can either stay in the same stratum or move from a stratum to a less deep stratum, so go with the poset ordering, but not vice versa. So in this way, then morphisms remember the stratification of X. So in the case of the Ron space then, it's the objects of this infinity category are finite non-empty subsets of M, and the morphisms are exiting or exit paths in the Ron space of M, which means that they witness anti-collision of points. So this picture illustrates a morphism in exit Ron of R2. So this morphism goes from this 2-point subset to this 3-point subset by anti-colliding exactly 1 point. Something to note about this morphism is that it is not invertible, because taking the inverse or the reverse of each of these paths would not give us an exit path in the Ron space. Okay, so in the case of Euclidean space, I've identified these infinity categories combinatorially as a localization of the full subcategory of the theta n category consisting of active morphisms. So Joyal's theta n category, I won't define it for this talk, but for the scope of this theorem, just take away the fact that it is an ordinary category and it's defined combinatorially. So in this way then, the configuration spaces of finite subsets of points in Rn are encoded combinatorially. So there are two conjectures that I'm presently working on, which are both generalizations of this result. The first uses the exit path infinity category of the Ron space to understand the configuration space of a product of manifolds in terms of the configuration spaces of the factors using the Reith product of infinity categories. The second conjecture states that the exit path infinity category of the Ron space for Rn with some decorations is a localization of the full category theta n. So this denotes the one-point compactification of Rn. This denotes pointed subsets, taking pointed subsets. And the U stands for unital, which means that we also consider the empty subset. So conjecture 2 indicates that the configuration spaces of finite subsets of Rn give insight into the combinatorics of infinity n categories. Because one way of defining infinity n categories is in terms of contravariant functors out of theta n. So in particular, it is conjectured that En algebras embed fully faithfully into infinity n categories. And conjecture 2 then yields an approximation of this conjectured functor. And let me precisely explain how. So first, functors out of the exit path infinity category of a stratified space X classify constructible sheaves on that stratified space. And constructible here means locally constant with respect to the strata of X. So this result was first due to McPherson with the exit path category, and then later due to Ayala, Francis, and Tanaka, and also Jacob Lurie for the exit path infinity category. Lurie also shows that non-unital EM algebras embed fully faithfully into factorizable co-sheaves on the Ron space. Factorizable means constructible, satisfying some properties. So then these two theorems together indicate that there's a functor from non-unital EM algebras to pre-sheaves on exit Ron of M. And I conjecture that this functor factors through pre-sheaves on exit Ron of M with the decorations, which is the infinity category that showed up in conjecture 2. So this arrow here is the forgetful functor induced by the fact that exit Ron of M is a subcategory of exit Ron of M with the decorations. So then this functor here fits into the following diagram here. And conjecture 2, observe that conjecture 2 would give us a fully faithful functor from pre-sheaves on exit Ron of Rn with the decorations into pre-sheaves on theta n. And in this sense then, conjecture 2 yields an approximation of Bn. Okay, so the other direction that I'm interested in heading using the exit path infinity category of the Ron space is towards finite type non-invariants. So given a knot K, there's an induced functor between exit path infinity categories. The previous theorem identifies the target of this functor in terms of the theta 3 category. And I've also identified the source of this functor in terms of the parasimplex category. So again, for this talk, I won't define this category, but just take away the fact that it is an ordinary category. So I conjecture that finite type non-invariants factor through the space of these functors. And this would be a powerful result because through the identification of the target and the source, we can apply factorization homology and capture each of these finite type non-invariants algebraically. Okay, so that concludes my talk. Thank you so much for your time.